Jai Hind, I am Sanjay Sonker, working as an assistant professor in AKGE Engineering College. In this lecture, we will discuss about the grammar. Is a part of the theory of automata and formal languages. Subject code is KCS 402. This is the second part of the lecture. Last time we will discuss about the grammar, how to, why we are study the grammar, why we interested in a grammar or in a theory of automata and formal languages. In the grammar, we used to generate a language, and language is accepted by the machine. We will discuss in last. Next we will discuss about the how to express the grammar, and next we will discuss about the definition of a grammars, how to define a grammar, types of a grammar. Express a grammar, that is the English language. We are just used to the sentence. Sentence is generate a noun phases, predicates, and noun phases is again generate a articles and nouns, and predicates is generate a verb. Here we will discuss the last. Same articles is terminate with a. Next the noun boy and dogs, verb runs and walk, that is a verbs. Now we drive a sentence using with the set of rules and also known as a grammar. Sentence is generated, noun phases, predicates, and noun phases is again generate. Noun phases is generated, noun phases, predicates is verb, and again noun phases generated articles and nouns and verbs. Articles generated the nouns and verbs. Noun is terminated with boy, and verbs is terminated with walk. That sentence is generated for a given grammar. That is a language to generate a generated by the grammar. We are simply classified the grammar is using with alphabets. Alphabet generate a word, and words is generate a sentence. Alphabet is a limited, words are also is a limited, is stored in a dictionary, and sentence is infinite, we generate through the alphabets and words. The notation of a grammar, here there is a nouns, that is a symbol, it's a variables, is also known as a non-terminer, that is a production rules, and boys and dogs is a termination symbol. Another example of a grammar, we are just used to define a grammar. S production is generate a S B, and S is generate epsilon null. Here is define a grammar is defined as a variables. S is a variables terminer. Here a terminer is small a, small b is a terminer, and epsilon lambda is also a terminer. Start symbols is S, and production rules is given as a S, generate a S B and epsilon lambda. Next we generate a language, generate a sentence from the grammar, is known as a derivation. Derivation is a process to drive a string. Now we use to the derivation, that is a grammar is given as grammar. S is a start symbol, symbols. So we start with derivation, A S B. Next S also generate as a production, A S B B. Next we use another production, epsilon. The string will be generated as A epsilon lambda B B. The string is A B B will be generated. The smallest string is a B. The language is defined as a epsilon, that's a start symbol. Next A B B, finite or infinite, language is a infinite will be generated for a given example. Now there is a notation how to define a grammar: vertex, variables, terminer, production, and start symbols. That is a V is a variable, is a finite set of a variables, T is a finite set of a terminal symbols, S is a starts variables, P is the production rules in a given grammar. Last lecture we will also discuss the type 0, type 1, type 2 and type 3 grammars to generate a language, correspondence language, and accepted by automata. Type 1, type 1, type 2 grammar we discussed already. Last lecture we discussed this. In this lecture we discussed the linear grammar, how to define a linear grammar. The linear grammar is defined most one variables at the right side of a production. That is, just take a simple example. That is a one S is a start symbol. There is another next right hand side have a one variable. S is a variable, same as another grammar. Right hand side have a only one variable. Right hand side only one variable. This grammar is known as a linear grammar. Non-linear grammar, if more than variable on a right hand side, this types of a grammar is known as a non-linear grammar. Now we check this non-linear grammar, which kind of language is generated by this grammar. Now we check it using with the derivation, and S generate SS. Next we are replace it as A S B S. Next again we check it, S is replaced with epsilon, A B S. Next S is replaced by this production is A B B S A. Now this S is replaced by epsilon, lambda, A B B A. This language is generated, this string will be generated through this grammar. Now we identify this languages, number of A and number of B's are same here. Now we check the number of A and number of B are same in this grammar to generate a language. Now another linear languages grammar is given. Now we check the language generated is A ki power n, B ki power n, or n is greater than or equal to 0. This is a linear grammar. Right hand side is only one variable, that is identify the grammar is a linear grammar. Now we check it to generate the language. S production is A production is AB, and B production is using with A B, and again A we are using to epsilon. So AB is the smallest substring of the generated this language, this grammar. We are using to the derivation or derivation tree. Derivation tree is the graphical representation of a generated string. Yes, that is a derivation tree. We just draw the derivation tree. S generate A generate A B generate A B, again A generate A B, next B generate A B. There is a number of A, left hand side is growth of the left hand side tree is a number of A, and right hand side growth of the tree is number of B's. That is a number of A is generated here and number of B is generated right side. Now we just read that derivation tree is a left to right. A ki power n, B ki power n, here n is greater than or equal to 0. Next, right linear grammar is given as a right hand side variables is the rightmost, that is a right linear grammar. Left linear grammar, right hand side variable is leftmost, that's known as a left linear grammar. The example of a left linear grammar, right hand side variable is leftmost of the grammar is known as a left linear grammar. Next, we discuss about the regular grammar. The regular grammar is any kinds of a right linear grammar or left linear grammar is known as a regular grammar. Regular grammar generate a regular language, and regular language is accepted by finite automata. Or regular grammar is classified as a two types. First is left linear and second is a right linear grammar. Now we take an example to identify the grammar is left linear or right linear. Now you observe this right hand side variable is rightmost. This types of a grammar is a right linear grammar. This grammar is a right linear grammar. Now second grammar we observe that right hand side variable is leftmost. This types of a grammar is known as a left linear grammar. Okay. Now we observe observation of a examples. Regular grammar is generated regular languages. Let's take an example G1. S generated A B S. Now we define a grammar. G1 grammar is defined as a variables S variables. Terminals is given here. A and B is a terminal, and start symbol is S. Production rules is given as S generated A B S and A. That is a defined as a grammar. Now we generate a grammar to the regular language. Now we check it. We just use to the derivation tree to identify the grammar, convert the grammar to regular languages. That's a S A B S. Now we again S recursive, call recursive grammar A B S, again A B S, and so on. S is terminated with A. S is terminated with A. Now we read this grammar derivation tree left to right. Read as a left to right. A B A B A B. That is a recursive, means A B star and A. It's a generate A B star A. Now again next check the grammar G2. This generated regular language. This grammar is generated regular language to using with the derivation tree S A B. Next we again use the production of A B. Next we are using production A B. That is a recursive, and A is growth with B, is a production of B, or B is terminated with A. Now we read this A and this is a B star. That's a recursive. So A B star and A B. That is a grammar is generated language. Now take another more example. Now here we consider the following left recursive grammar and convert them into the regular expression. Now we just take a example 1, that is a left linear grammar. First we identify the grammar here. This grammar is a left linear. Why? Because the right hand side variable is a leftmost. This types of a grammar is known as a left linear grammar. Now we just this grammar is convert to the regular expression. Now just take a using with derivation. We draw the derivation tree. A generate A. Next A is generated A is generated A, and so on. That is a recursive A star, and next terminate with B. A is terminated with B. Now we read left to right, reading as a left to right. The left to right B A star. That is a regular expression. Regular expression of a given grammar. Take another example. Now we observe this example. Here is terminate A, terminated with A and B. There is a two choice to terminate the grammar. So we just use to drive a derivation tree. A again generate A and A is terminated with B or C. A is terminated with B or C, that is a recursive. A star and is terminated with, there is a two choice, B or C terminate. Now we just read left to right, B plus C, there is a two choice to terminate the grammar, B plus C and A star. That is a regular expression for a given grammar. Now take another example to consider the left recursive grammar and convert into the regular expression. Now we observe that there is a two choice on a recursive. There I have a two choice on a recursive. Now we just take a example. A generate A, next A generate A generate B, have a two choice, A generate B, we have a two choice A plus B as a recursive and terminate with C. Now we read it left to right, C, and we have a two choice, A plus B star. Closer. Clear? Now we take another example 4. How to solve it? There is a recursive S01 as production is given as generate. Next again S production is 01S, 01S, or S is terminate with, and so on. S is terminate with 01. Now we read it. There is a 01 as a recursive and 01. Now we read it left to right, 01 star and 01. That is the regular expression to generate with grammar. Another example, same as we have a two choice to terminate this grammar. Now we just generate a regular expression for a given grammar is 0011 S, again recursive 0011 S, next 0011 S, and is terminate with, there is a two choices option 0 and 1 and 1 and 0. You have a two choice to terminate. Now we read this left to right, 0011 star, and we have a two choice to terminate 01 plus 10. That is a regular expression for a given grammar. Now if we take an example 5 to solve, how to solve this example. Now we have a two choices for a recursive, that is a right linear, next choice has a left linear grammar. We have a two options here given as a left linear, right linear options will be given. Now how to solve these types of problems? First we take a one grammar as a drive a derivation tree. Now S generate 01 A, next we check another A production is given as this one A 011 A and recursive 011 A and so on. Now A is terminated with 01, so A is terminated 01. Now we read it grammar left to right, there is a 01, that is a recursive 011 star, this is a terminate 011 star and 01. This is the regular expression for a grammar. Next the second part is left will be completed, and next will be again next production is a S B 11, B is given as a production is generate 101 B 101 B 101 B and so on, and terminate with 1. Now we read it left to right, that is a 101 star 11 and 11. Now we have a two choice given here. The final regular expression is given as a we are just combined. There is a two choice. We just combine them. 0 1 0 1 1 star closer 0 1 plus 1 0 1 star closer 1 1 1 1. That is a final regular expression for a given grammar. Now there is a very important question. How to solve these types of problems? Same as we have a two choice here. We just same procedure to solve it. Drive a derivation tree. S generate 0 1 1. A production is given as 1 1 0 A, and that's a recursive call, and it's terminated with 0 0. Now we read it left to right. That's a 0 1 1. That's a recursive. 1 1 0. That's a recursive. 1 1 0 star 1 1 0 star and 0 0. Next of choices, S generate 0 1 0 1 B. B production is given here. Use this production. 1 1 B, again 1 1 B, 1 1, and terminate with S. That is a recursive. 1 1 star, that is a recursive. Now we read this expression. That's a 1 0 1 1 1 star and S. The regular expression is defined as a expressed as a 0 1 1 1 1 0 star 0 0 plus combine them 1 0 1 1 1 star S. Now we observe that is a that's a beta, that's a terminal, and this is a alpha, and that's a S. Now we just combine them, is it defined as a. Next we just check it, same as grammar is new grammar is generated as a defined as a. So new grammar is a alpha A and beta. Now to solve same procedure, we just solve it. That is a right recursive grammar and terminate with beta. We directly solve it as a terminate with beta. So just solve it directly. We are just using here to solve it 1 0 1 1 1 star ka whole star and terminate with beta. 0 1 1 1 1 0 star 0 0. That's the final expression of a given grammar. Okay. Next we discuss about the theorem. Language generated by the regular grammars is also a regular grammar. Subset of equal to, if a grammar is generated, language generated by the regular grammar is a subset and equal to the regular language. Any regular grammar is generated a regular languages, and another part is any regular grammar language is generated by a regular grammar. Now we discuss about the another concept here. Now next question is based on a regular grammar to the finite automata. How to draw the regular grammar to the finite automata? Now we just take example. That's the grammar is a given and generate a finite automata. A finite automata maybe is a generate a NFA. Now we just take example. S is a start symbol. That is the initial state. That is the initial state. S is the initial state. It's take a input 0 and reach to the state S1 and take a input as a 1 and reach to the S. and it's take a 1 and it's a reach to the epsilon state is a finite state. Let's say convert this grammar is converted into the finite automata. Now we just use to convert the regular expression for a finite automata. The regular expression is given as a 0 1 0 1 0 1, that is a loop. We loop and terminate with 1, that is a regular expression. From the regular grammar to finite automata and finite automata to regular expression. In this question we will discuss about to the regular grammar to finite automata and finite automata to regular expression. We just easily conversions. We just simply use to the regular grammar to the regular expression to the regular language. We just conversions, and regular languages to the finite automata and finite automata to regular expression to regular grammar. Same as another, we take example. Now we take another example. Given grammar to convert the finite automata, we just take a compare. This start symbol is the initial state in a finite automata. S is the initial state in a finite automata. It's take a input 0 and reach to the new state. It's take a 0 and reach to the new state 1 1 s. Again it's take a 1 input and reach to the new state 1s, and it's take a input 1 and reach to the state s. Okay, next, that is a terminate 0 1 0, it's take a 0 reach to the state. Next it's take a 1 and reach to the finite state, that is a epsilon state. That is a finite automata. Design a finite automata. Now we just convert the finite automata to the regular expression. Here we just observe that there is a start with start symbol, that is initial state s 0 1 1, that is a loop. 0 1 1 0 1 1, that is a loop. 0 1 1, we just read it and reach to the initial state and goes to the another path 0 and 1, that is a finite state. That is string is generated. Now we are just stop here and continue to the next lecture to more discuss about to the grammar to the finite automata. Thank you.